Morning everybody. Today what we're going to be looking at is the exponential form of a complex number. So we're going to draw on the things we've learnt in the Maclaurin series chapter first. And in front of you at the moment it says e to the x equals 1 plus x, etc, etc. And that's the Maclaurin expansion of e to the x. So what I'd like you guys to do is, can you just substitute in I theta to this? And once you substituted in I theta, you might need to do a few more terms than I've done, maybe up to about 6 should do it. Can you have a quick look at organising what you find into real parts and imaginary parts, and have a look back at the Maclaurin series notes for see if you notice anything particular about from what we did then. So just pause the video please, expand this out and have a go at that. So hopefully when you expand this out, oops, I'll just pause this and do it. Hopefully when you stuck I theta in, you got what we have here, and if you just change this slightly by evaluating what's in those brackets, you should get this. And separating those into imaginary and real parts, you get, and hopefully you've noticed that we've got two bits here, one which is the Maclaurin series for cos theta and one which is a Maclaurin series for sine theta. So e to the I theta, this first bracket here, is cos theta plus I lots of, and this bit here is sine theta. So in other words, the exponential form of a complex number z, so if z is equal to cos theta plus I sine theta, then we can also write z as e to the I theta. One thing you may have noticed from there is that there's no modulus involved, but if I times the top one by r, then I can times the bottom one by r as well, to get a different complex number with a modulus that isn't 1. So it could be r e to the I theta. And if you were asked now to prove De Moivre's theorem, hopefully you would actually use this instead, because it makes the whole thing 3 lines long instead of having to do it by induction. Okay, so what I'd like you to do is just have a quick go at a few questions converting into exponential form. So can you guys have a go at question 1, 2 and 3 from 10.4. Once you've done that, can you come back to the video so we can have a look at summing some series. Okay, so just before we get on to evaluating series, not summing series, a series is a sum of a sequence, we need to just look at two quite important results. So here we've got e to the I theta is equal to cos theta plus I sine theta, and it should be e to the minus I theta equals cos theta minus I sine theta. If you don't believe me on that one, then just stick a minus theta into the top one and think about the symmetry with cos and sine and see what happens there, the odd and even functions. Okay, so using what's in front of us here, we're going to prove an important result for cos theta and for sine theta. So first of all, let's just have a look at trying to work out something for cos theta. So what I'm going to do is I'm going to add 1 and 2 together. If I add 1 and 2 together, I'm going to get e to the I theta plus e to the minus I theta is equal to, well, the coses add together to give 2 cos theta, and the I sine theta and the minus I sine theta cancel each other out. Therefore, cos theta is half of e to the I theta plus e to the minus I theta. Okay, so what I'd like you guys to do is, can you do something similar for sine theta, please? Can you try and find out what sine theta is in terms of the exponentials? Just pause the video. So if you subtract them instead of adding them, you get e to the I theta minus e to the minus I theta equals 2i sine theta. And so therefore sine theta is equal to e to the I theta minus e to the minus I theta all over 2i. Okay, so these results are both really important, and you need to be able to prove these if asked to do so in your exam. Okay, so remember those 1 and 2 at the top there, and remember that you just need to either add or subtract to get cos theta or sine theta. Okay, so we're going to start evaluating some series now, and this is the first bit of the question. It says prove that 1 plus e to the I theta is equal to 2 cos theta over 2 e to the I theta over 2. That exponential isn't in the cos bracket. Let's just put a bracket there, just so we know what's what. And these questions normally will start with some proof like this, and the second part of the question is you'll need to use this to evaluate a series. There's 2 ways of doing this, and I think this is arguably some of the harder stuff of the course until you get used to it. What you can do is you could split that into coses and sines and then use some double angle formulae to get what's on the right hand side. Or I think the more efficient way is by looking what's on this side over here and thinking about what the angles are. The angles in this case are all divided by 2. So it would be really useful if we could write the right hand side in a similar fashion with thetas over 2. So what we're going to do is we're going to do just really some sneaky manipulation. Okay, so first of all, I've got 1 plus e to the I theta, and then I'm going to do something really sneaky with the 1. I'm going to say 1 is e to the I theta over 2 times e to the minus I theta over 2. Let me just underline some of those bits. So that 1 is that bit. If I times those two things together, I add the indices, I add those indexes, I get 0, e to the 0 is 1. And then with the next bit I'm going to do something similar. So e to the I theta is e to the I theta over 2 times e to the I theta over 2. So we've got 2 bits here, and what I've done is I've changed my original thing into something which has got theta over 2's all over the shop. So I know from looking at the question I'm trying to prove that the left hand side equals the right hand side, and the right hand side is just one term. It's 2 times something else. At the moment I've got 2 terms, so I need to work out a way of getting 1 term. And the simplest way of getting 1 term from 2 is to do some factorising. And you can see the first term in both of these is e to the I theta over 2, so I can factorise an e to the I theta over 2 out. And I'll be left with e to the minus I theta over 2 plus e to the I theta over 2. So what I've done is I've just factored one of the e to the I thetas out. If I just rewrite this ever so slightly, the I theta over 2 bracket e to the I theta over 2 plus e to the minus I theta over 2. Hopefully you'll see or remember from the previous page we've got this situation here. I've just got that bit in my bracket here, and this is equal to 2 lots of cos theta. So I can write this as 2 cos theta e, try that again, it's not theta is it, it's theta over 2 now, cos theta over 2 e to the I theta over 2. And that's what we're trying to show. So we're done. So just before we go any further, all of these things, whenever we've got to prove this sort of stuff, the key is to look at what's going on here. If you've got theta over 4 or theta over 5, whatever it is, whatever's here, you need to make the left-hand side have loads of those as well, and it will normally come out in the wash. You can change the left-hand sides to sines and cosines and use double angle formulae, that will normally work. However, I think it's generally harder to spot. Okay, let's have a go at this one then. So show that the sum of the series 1 plus, let me just write those a different way. So I'm not sure if you guys are used to seeing it like that. So n choose 1, I think you'll normally see it like that instead, n1. Okay, so we're going to show that the sum of that series is 2 to the power of, oh crikey, why did I take a picture of this thing? Right, let's scrub this. Okay, that's better. So 2 to the n, cos to the n, theta over 2, and then cos n theta over 2. So we're going to try and show these things to be true. Okay, it's not really easy to see at all where to start with this. Hopefully you get a bit of a whiff of binomial expansion about it. Hopefully you also get a bit of a whiff of De Moivre's theorem because of the multiple angles. So let's just quickly write down or remind ourselves what De Moivre's theorem says, at least in terms for exponentials. So in terms of exponentials, if I've got e to the I n theta, then that's going to be the same as e to the I theta n to the power of n. If you think, oh, where's that come from? Expand the left-hand side out. Write the left-hand side in terms of coses and sines. Write the right-hand side out in terms of coses and sines, and you'll just see De Moivre's theorem straight away. So what we're going to do to answer this question is introduce two series. We're going to introduce a series C, which is 1 plus n choose 1 cos theta plus n choose 2 cos 2 theta plus n choose 3 cos 3 theta dot dot dot. And that's just what we want to show actually. We're also going to introduce another one as well. We're going to call it S, and that's going to be 1 plus, not 1, let's try that again. It's going to be n choose 1 sine theta plus n choose 2 sine 2 theta plus n choose 3 sine 3 theta dot 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 dot. Now what I'm going to do is I'm going to add these things together, however I'm going to times s by I. So in other words, I've got C plus IS, and that's going to give me 1 plus n choose 1 cos theta plus I sine theta plus n choose 2 cos 2 theta plus I sine 2 theta plus, and it just carries on and on and on. Converting what's in the brackets to exponential form, this becomes 1 plus n choose 1 e to the I theta plus n choose 2 e to the I 2 theta. I carry on going, n choose 3 e to the I 3 theta. It's normal to write the number at the front, but just to make the point that it's 3 lots of the angle. And hopefully you can see from here that if we use de Moivre theorem, we can convert those to 1 plus n choose 1 e to the I theta plus n choose 2 e to the I theta squared plus n choose 3 e to the I theta cubed. And these things keep going. And hopefully you'll recognise that the right hand side is now written in the form where you can easily see that it's a binomial expansion. We've got a term which is 1, and then we've got the coefficients coming in here, 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 etc. And then each of these has a power raised every time, etc., etc. So it's the binomial expansion that you guys have learnt this year in your A level. So therefore we can write this as C plus IS is equal to 1 plus e to the I theta to the power of n. And if you don't see that straight away, then just expand this right hand side out and check that it is indeed the bottom line there. Okay, so when I first saw this, I think I probably got to this point of the demonstration and thought, big whoop, how's this got any closer? So let's just, if you haven't seen it already, hopefully you have, let's just see how we are going to get on. So remember that we wanted to show that the sum of the series 1 plus n choose 1 cos theta, etc., 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 is equal to 2 to the n cos to the n, etc., etc., etc. In other words, we wanted to show that C, because we decided to call it C, is equal to 2 to the n cos to the n theta over 2. And we can see that what we could do is just take the real part of both of these sides, and that would get us to where we want to be. So the real part of 1 plus e to the I theta to the power of n. Now that doesn't seem to be overly useful until we remember that we did a part A. Remember in part A that we proved that 1 plus e to the I theta is equal to 2 cos theta over 2 e I theta over 2. So I can substitute that into what I've got here. So this is equal to the real part of 2 cos theta over 2 e I theta over 2 to the n. So bringing the n exponent inside, I actually just want the real part of 2 to the n cos n theta over 2 e to the I n theta over 2 and if you get stuck at this point, you're saying to yourself, how does that help? Remember that the last bit of this is currently in an exponential form, and we don't want any exponential form stuff in our answer. So if I now write that last bit in terms of cosines and sines, I want the real part of 2 to the n cos to the n theta over 2 cos n theta over 2 plus I sine n theta over 2. If I expanded this bracket out and just took the real part, that would give me 2 to the n cos n theta over 2 cos n theta over 2. And that's exactly what I wanted, I think. Yes, it was. Yep, good. So this is a really long process, or feels like a long process, but introducing this C and this S early on, obviously we could have been looking for S instead, and if we were looking for S, then we'll be taking the imaginary parts when we get to this bit. And then adding them together, you're trying to get yourself to a point where you can write something as a binomial expansion. And because of the multiple angle identity, the multiple angles in the question here, you need to use de Moivre's theorem at some point. But after you've used de Moivre's theorem, you should be able to get a binomial expansion, and then you just take the real or the imaginary part as is required. Quite often the crux of the question is this bit, and then the hardest bit about this stuff is remembering what to do. Okay, so some exercises I'd like you to do. Exercise 10.4, questions 6, 5 and 4. I've written that way around because I'd like you to do them in that order. And just a quick note about question 5. Question 5, so question 6 is another binomial expansion one. Question 5 actually ends up being a geometric expansion instead, a geometric series. So one thing which will probably come in handy because you haven't seen this yet because we're in the sequence of the chapter, is that the sum of some geometric sequence is a1 minus r to the n over 1 minus r. A is the first term of the sequence, and r is the common ratio. And I think that should be fine for that bit. That should be okay otherwise. Email me if it doesn't work out. And question 4 is revisiting some roots of complex numbers, which is quite a good question. Okay, so have a go at those, please, guys. Email me if you're struggling with anything, and I'll speak to you again tomorrow. Thank you. Bye-bye.